So question number 2 reads, says, most function can be arranged in several ways to give it x is equal to g of x. So remember that when we are dealing with fixed point iteration method, you have to make sure that the function, okay, given to you, you have to arrange it in terms of x is equal to g of x, right? What do I mean is that you have to arrange the function in different ways, okay? And it also depends in what way you're arranging your function, okay? And that function is going to converge. Okay, so you always have to arrange the function in terms of x is equal to g of x. Let's say I have the function like x cubed plus 3x squared plus x, right? Minus 2. Let's say this function is equal to 0. So we have to solve for x, isn't it? Okay, so there are different ways. So the first way we can do it is by just solving for this x, right? So by moving x to the other side of the equation, you're going to have what? Oh, sorry, moving the rest of the term to the other side of the equation, you're going to have 2 minus x cubed minus 3x squared minus x. So now this function now becomes x is equal to, this is now our g of x, right? G of x. So you've written in form of what? X is equal to g of x. If you want, you can solve for x cubed. Okay, so if you solve for x cubed, you notice that you're going to have what? X cubed is equal to 2 minus x minus 3x squared, right? And then if you take a cube root of both sides, you're going to end up having what? X is equal to the cube root of x2 minus x minus 3x squared, right? And then power 1 over 3. Okay, if you want, can you solve for x squared? So based on the different arrangement that you have, you see that it depends, okay, which arrangement is the best for you for convergence. So if you want to check it's converging on that given interval, remember that we looked at those conditions, okay? So you can check which one converges if you are given the interval. Okay, so by doing those tests we were doing last time, you arrange your function, you find out, you can find out, okay, which arrangement is it the best. Okay, the one which is the best arrangement, the best arrangement is the one that converges in that given interval when you apply those conditions we looked at yesterday. Okay, so sometimes it's not always that the function will always be given to you in this form, x equal to g of x. Sometimes maybe be required, okay, to write in the special form in a good way, okay, in a way that the function is going to converge. So you can try a couple of different arrangements and then you test them on that given interval and then you start doing your iterations. Okay, so we look at this now. So let's look at the question that we have here. So the sentence says the most functions can be rearranged in several ways to give x is equal to g of x, right? Which, okay, with which to begin the the fixed point method. For f of x is equal to this, okay? So we're given the function, okay? For f of x is equal to e to the power x minus 2x squared, and this is equal to 0, okay? 1 g of x is so we're told that 1 g of x, meaning the arrangement of this, one of the arrangements that we can produce from this is x is equal to plus or minus the square root of what? A to the power x over 2. So you can see that, oh, we got this arrangement by solving for, which one did you solve for? We solve for x squared, as you can see. So when you solve for x squared from this equation, this arrangement that you get, okay? So now this becomes x is equal to g of x. So our g of x is what? This guy, right? So I've managed to arrange that equation in the form of x is equal to g of x. Okay. So this is it, x is equal to plus or minus g of x, right? So you can see that this is our g of x by just solving for that, isn't it? We've solved for x squared. So how do you do that? X e to the power x minus 2x squared equal to 0. Okay, so by taking 2x outside or by just switching these two, you have 2x squared is equal to e to the power x. If you divide by 2 both sides, you have x squared equal to e to the power x over 2. If you square both sides, take a square root of both sides, you'll notice that this is what you get now, right? As x is equal to plus or minus the square root of e to the power x over 2. So this is exactly what you have here. So that's one arrangement, okay? All right, now with this arrangement, what is it saying? So the first question says, show that, okay? Show that this converges to the root near 1.5 if the positive value is used, and to the root near negative 0.5, okay, if the negative value is used. So the question says that show that, so to show that this x is equal to plus or minus the square root of e to the power x over 2 converges, right, to which value? 1.5 when x is equal to g over x. What I mean here is that positive g over x side, and converges to negative 0.5 when x is equal to negative g over x, meaning when this function is what? Negative, right? So that's what you need to show. Okay, so now when you're doing it with fixed point iteration method, this is the order you need to follow, right? Okay, so you need to find the root. The next root is equal to the function substituting the previous root. Okay, so this is how you do the fixed point iteration method, right? P of n minus 1. So what it means is that, remember that we are solving the equation, so we're looking for the root, right? So to find the root, okay, you need to substitute what? The initial root in the function. So to find the next root, you're going to use the previous root that you found, okay? So let's look at this example given for better understanding. So in this case, okay, we have to show that, oh, we are using 1.5, we are converging to 1.5, right? Okay. If we show that this function converges to 1.5 when x is equal to g of x. So what you need to do here now is just start doing the iterations. And how do we do those iterations? Okay. We have to start doing the iterations, and how do we do that? So we're going to use the formula which is given to us. Okay, so we are given the formula, and from this formula now we can apply it. Okay, so let me just show you how you can do this. Okay, what I'm going to do here, I'm going to use just values that are close to 1.5. Let's see, by doing that iteration, let's see if we're going to approach 1.5. Okay, instead of using the actual 1.5. So 1.5 would be more like a reference to us. Okay, so what I'm going to say do is, okay, so I'm going to let's do about, how many iterations will we do? So this will be n value. What I'm going to do here, I'm going to pick a couple values for n. N means like, okay, different iterations, right? So I'm going to say, okay, n1, n2, n3, n4, and all that, right? Okay, so different values of n, and also differently, I'm going to get different values of what? P. Okay, so I'm going to get different values of what? P. So this will call, I'll call it P of n. So let me just make a box. Okay, so what we're trying to do is that as we are doing the iteration, let's see if our values are coming close and close, I mean as close as possible to 1.5. So all the times for you to not waste much of the time, make sure that your initial value you pick must be very close to 1.5. Okay, you have to pick the initial value which is very, very close to 1.5. Okay. Okay, so I have to pick the values that are very, very close to 1.5, right? So if you look at 1.5 here, what value can we pick which is very close to 1.5? Okay, so that would be the starting value. So n equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, 7, 8. Okay? All right, so now let's start. So for n equal to 0, this will be P naught, right? P 0. So I'm going to choose my P0 to be what? Oh, my P0, I said, okay, let's pick the value which is very close to 1.5. Okay, so I'm going to pick, okay, we can start with a 1, it's fine. Okay, let's start with a 1. Okay, let's start with a 1. Meaning the value of x is equal to 1, starting point. So as we'll be doing iteration, are we approaching 1.5? Okay, so I'm going to start with 1. And then we're going to find what value am I going to get after first, second iteration. Okay, after first iteration, second iteration, third iteration, fourth, and so on and so forth. Okay, so this is my equation. X is equal to the square root of e to the power x. So I'm using the positive value, right, over 2. Okay, so since it said, oh, we have to show that we are converging to 1.5 when using a positive value. So, and this is a positive value we're using. Okay, all right, so let's start. So x1, so we're going to say, okay, we're going to find x1 when n is equal to, okay, 1. So remember that this one always needs initial condition. So this will be our x1. In fact, let me just, instead of naming this as Pn, let me name it as Xn instead. So using X, right? So this will be Xn. So my X1 will be equal to, so I'm going to substitute the initial condition that I have. So I've chosen the initial condition with X not equal to what? 1. I've just picked 1. Okay, so this is my initial condition as X not equal to 1. Okay, so let's substitute. In place of X, putting a 1, that will be my first iteration. So e to the power 1 over 2. So what is my x1?
It's 1.165.
1.165, yes. 821, something like that.
991.
Okay, 08. Okay, me avoid something like that. Okay, it's okay. So this is now your x1, right? So you're going to put in a, so my what is very small, just be rounding it off. But when you're putting it in the function, please don't round off. So here I'm going to put the rounded off value 1658. Okay, all right, like that. And then let's go ahead and get x2. So x2 will be equal to the square root of, now we're going to use what? The previous value found for x. So this will be e to the power 1.165.
1.2666.
Okay, 1.2666.
01.
01.
596.
596. Okay. All right. So this is our x2. So it means that our x2 is 1.2666 something there. And then let's find x3. So e to the power 1 point. Now we're using the previous value 266 over 2.
1.33.
Okay, 1.33.
206.
Okay, let me just, okay, 1.33. Okay. 206.
0788.
Okay, 0788. Okay, so this is a 1.33 to whatever. Okay, so that goes. And then what is x4? So using the previous value, which is e to the power 1.33, 2, and then divide by 2. Okay, so make sure that you put all the whole of this value here.
1.376.
1.376. Okay.
37. 9917.
9917. Okay, so this is 1.376, something like that. Okay, and then let's find x5 when n is equal to 5. So again, this is e to the power 1.376. Okay, and then 3 whatever there, and then divide by 2. So what is that?
1.407.
1.407.
220.
220.
339.
339. Okay. So you can have that is 1.339. 407 something there. And then x6. So as you can see, we are actually approaching this, right? Okay, we're actually approaching that. Okay. Over 2, how much do you get?
1.42
1.42
9088
9088. Okay, like that. Okay,
144.
144, right?
Yeah.
Okay, so you can put x7, have x7, so this is 1.42. Okay, so as you can see, we are still approaching 1.5, right? Okay, and then if you put that 1.42 over 2, so how much do you get as x7?
1.444.
1.4, how many fours? 4, 3?
Yes, and then 799
799
39.
39. Okay, so this is 1.444. Okay, and then x8. So this is e to the power 1.444 something over 2. Okay, so we're having a lot of iterations because we started from very far from 1.5. If we had picked value like a 1.3 or 1.4, close to 1.5, would have converged by now. So it just depends on what is your initial value starting from. So always pick the value which is very close to your root, okay? So what do you get here?
1.45
1.45
61
61
93887.
9388. Okay, so you can continue. Now, this we're going to approach this value from one side. What if we try to approach it from the other side? Look at this, okay? You have 1.5 here. So we have approached it starting from the smaller values of x. And then you can see that we're approaching 1.5, okay? Starting from the smaller values of x. Okay, so as x goes to infinity, as you increase the value of x goes to infinity, g of x approaches what? 1.5, okay? Or that function approaches what? 1.5, as you're increasing the value of x from this side. Now, what if we approach it from this side? Okay, taking the limit, okay, as x approaches infinity. And then here, let's also take a limit, okay, as x approaches what? Approaches 0 this side, right? Okay, limit as x approaches 0, meaning that you start with a higher value, okay? The value is greater than 1.5. Are we moving away from 1.5 or approaching 1.5? Let's try a few values that are close to 1.5, but greater than them. What value can we pick as initial value, please? Let's choose the one which is close, very close, so don't do a lot of iterations.
59.
Okay, 1.59. Okay, it's fine. We can choose 1.59. Okay. So if using x naught, because what I want to show that okay, we're approaching. It doesn't matter which side you started from. You should have always approach 1.9. I mean 1.5. Choosing x naught equal to 1.5. Let's see. 1.59. Okay, let's see if we're approaching 1.9. What if we make it 1.6 just? Let's make it 1.6, I think.
Yeah.
Okay. Let's make it 1.6. Okay. So if we make 1.6, let's start what first value we're getting. So we're going to say x1. This will be equal to e 1.6 over 2. So I think the value that we're supposed to get here should be less than 1.5. I mean, should be less than 1.6 itself. Are you getting that? Are you getting something less than 1.6? Because if you get something greater than 1.6, then we are diverging.
1.57.
So you see that we started with 1.6, but we are getting something less than 1.6. 1.57 what?
36
36
95080.
Okay,
9502.
Okay, whatever you have there. Okay, so as you can see, we started with it at 1.6, right? So it means that as we are starting from the half value here, approaching 1.5, the value is actually decreasing. So around at 1.6, we find ourselves at 1.5 something, right? So we actually approaching 1.5 itself. But if in the case where we start with 1.6 and then you end up having 1.7 some as the initial as the x1, then we can say, okay, this is diverging. We're moving away from 1.5. Okay. So we started with the lower value of 1. We're approaching 1.5. We have shown these values here, as you can see. Okay, we decided, okay, let's start with a half value 1.6. And again, you can see we're also approaching 1.5. We are moving towards 1.5. Okay. So by doing more and more iterations, you discover that, oh, we're actually approaching 1.5 starting from either side of 1.5 itself. Okay, we are still approaching it. Okay, so what will be our x2? E to the power 1.5. So we should get something less than 1.57 this time around, because we are trying to approach that root, right? Okay, over 2 to the power 1 over 2. So what are you getting?
1.553.
So you see that you're getting something small, right? 1.553. Okay. Finish it. 3 what?
132642.
2642. Okay. So this is what you're getting. Let's do 2 more. What will be x3? So e to the power 1.553 over 2 in the square root. So what is x3?
1.5372.
1.5372.
46.
46.
349.
3 4 what?
9.
9. Okay. So let's do the last one. x4 e to the power 1.5372 over 2 to the power 1 over 2, right? Okay, so this is equal to what?
1.525.
Okay, so as you can see, this value is reducing, sorry. Okay, 25.
084. 143.
143. Okay, so you can try the rest. You see that if you get, as you are increasing the values, like as you are starting from the higher value of x, you are still approaching 1.5. You start from the lower value of x, you are still approaching 1.5. Okay, so it doesn't matter which side. So this is the 1.5 as our root. Okay, so if you approach it from this side, okay, we are still approaching the same root. Starting from this side, we are still approaching the same root. Doesn't matter. So here, starting from 1.6, we are still approaching it. Here, starting from 1, we're still approaching the same root, 1.5. Okay.
I've got a question.
Yes, please.
So when choosing the starting value, do some questions specify where we're supposed to start from, or we just have to use any arbitrary value that's close to the value we're looking for?
Okay, so in this question, if you notice, we were given like, it's like more you're given the root of the equation already, the solution for the given equation, right? So, okay, the answer is 1.5, but we have to show that, okay, as we are doing the iterations, we're actually approaching to that answer 1.5, right? So you'll notice that since in that case, we're already given the value or the solution to the equation, then you have to choose the starting value, the initial value, which is as close as possible to the what? To the given solution. Okay, if you can choose any value if you wish, but remember that the far part these values the value is from the solution, the more the iterations you are supposed to do. But it will still converge, but you have to do a lot of iterations.
So if I chose 1.1, 1.2, 1.3, 1.4 as
It will
my
still be
last
okay.
one, that's okay.
It will still be okay, yes. Because you still be
Alright.
approaching that, okay? So if you chose 1.1, you are going to do fewer iterations as compared to when we chose 1. Because now already you're about 0.4 difference between the initial condition and the 1.5 itself. So you just move few steps and then you find you converge to that answer. If you want, you can even start choosing from -1 or -2. Now look at the difference, the distance between -2 and 1.5. So you have to do
Yeah.
so many iterations, right?
Yes.
Oh, yes.
Yeah.
All right. Thank you,
Excuse me,
sir.
mate.
Yes, please.
Yes, what if you just start on 1.4? What happens?
Yeah, it's fine. You can just start from 1.4, okay? It's like it's very much open here, okay? You can start from 1.4 and then you're going to converge very quickly, right? Okay, you can even, but you have to show both sides, right? Since now we know the root is given to us, so we have to show that, okay, if we approach it from this side, we are still converging towards 1.5. If we approach from the left or from the right, we are still moving towards 1.5. Okay, so you can finish actually, can show actually at the end, you see that you're going to find almost 1.5 as the answer as we are doing more and more iterations. Try to find x9, x10, x11, x12. You see that you'll be getting closer and closer to 1.5. Is that okay?
Yes, sir.
Okay, now we also have to check now for the other condition, right? Saying, okay, we have to show that we are actually, when we use a negative, okay, when we use x is equal to negative g of x, we actually approaching what? X is equal to what? 1.5, right? No, sorry, negative 0.5. Okay. Let's see if we actually converge into negative 0.5. So here you can pick the initial values, okay, that are close to negative 0.5. So I'm going to choose, okay, let x is equal to x naught. This will call my x naught. So from the left-hand side, okay, which one should that be?
0.1.
I said left-hand side.
Oh,
Negative what?
0.6.
Oh, it's too close. Anyway, let's choose negative 0.6, yes. And then from the right-hand side, this, okay, we'll come back for right-hand side. Okay, so this is from left-hand side, right? Left-hand side. So let's see. And then from right-hand side, what should we choose? What should be the x naught? Negative 0.4, 0.3. Okay, let's say negative 0.3, isn't it?
Mm-hmm.
Okay, remember that negative 0.5 is somewhere here in between. So from here, say negative 0.3. Here it's negative 0.6. You guys have chosen negative 0.6. So we see if we are converging negative 0.5 in both cases. Okay, so let's check. So let's start the iteration. So it means that we're going to get the negative root, negative part of it. So we're going to use negative root now. So e to the power x over 2. So our x1 will be equal to negative root of e to the power. So we've started with what? Negative 0.6 over 2. So what is that? E to the power negative 0.6 over 2, the square root. That's negative what?
0.523.
Negative 0.8. So we're too close. I think 0.6 is too close. Negative 0.5.
23.
Uh-huh.
83.
83.
7587.
7587.
5.
Okay. Something like that. And then let's get x2. So now it will be negative, the square root of the same value that we found, which is e to the power now negative what? Is 0.5, 2, 3, whatever there, divided by 2.
0.544.
Negative 0.544.
544. 17.
Mm-hmm.
06.
06.
513.
513. Okay. Let's see. We want to confirm something. 383 75 875 Okay. Over 2. Okay, all right. Okay. Let's do x3. Mm-hmm. Mm-hmm.
0.53
0.53866
53866 63
63
503.
503. Okay. And then x4. Mm-hmm.
I don't know why it has increased.
It has increased. It has increased to how much?
Yes, to
0.54.
0.54.
Yes, it's a pattern. Let's see. We're going to come up with a reason why like that. Let's see. You are doubting why it has increased. Huh?
Yes.
Okay, let's move. So you see that it's actually changing, right? Here it has reduced, it has increased, reduced, increased. Okay, so it's more like a roller coaster, right? Okay, let's look at x5. How at some point to become stable? What do you have?
53.
Negative 0.53.
Yes. 975
975
0096.
0096. Okay, roller coaster, right? x6. Uh-huh.
Um 0.53
Negative 0.53.
985
985
826.
826. Okay, so it seems like it's still just swinging, okay, between those points, right? Okay, but doesn't mean you are diverging. This is diverging or converging? Okay, what's the next value?
Negative 0.5398
Okay,
290
negative
0.5398
0.5398
290
290
709.
709. So if you notice, now it has become stable, right?
Yeah.
x8, what to be x8, e to the power negative whatever there, over 2,
0.5398
negative 0.5398,
98 6
sorry,
36
36
952.
952. So if you do as many iterations as possible, you notice that this, as you can see, 5398, 5398, okay, 5398, it's more like it's constant. Okay, so you have to do a lot of iterations, of course, but you'll be approaching negative 0.5, but at a very slow rate. Okay, as compared to this one when approaching 1.5, it was very fast, but this one you're approaching 1.5 at a very, very slow rate. So yes, the convergence is there, on that it's at a very, very slow rate. Okay, so if you choose the other side also, if you choose negative 0.3, I think the same thing also will happen. Okay, we'll be trying to approach 0.5, but at a very, very slow pace. So let's see. So what will be our x1 if we choose negative 0.3?
0.6, negative 0.608,
We got 0.6,
08, 16,
16,
0.8, sorry, 612.
8612.
Yes.
Okay,
4468
or whatever. What will be x2?
the exam.
Sorry.
You can get tired.
Yeah, it's to do it.
0.521,
521,
58,
58.
66757.
Okay, whatever. So you see that here we're also having the same behavior of approaching negative 0.5, somewhere there, towards 0.5 at least. Okay. So how much is this?
0.544.
Okay, so there's a swing, right? 4, as you can see, there's a swing.
783
783
4361.
4361. Okay. All right. So let me see, because I don't know how the behavior of this function is. Can I get something out of it? Let me see if it's possible. Okay, let me check. I've never seen how this function looks. Maybe I'll be able to understand why it's behaving like that. Let's see if this is the case. Oh, let's see. Mm, okay, e to the power x. Okay, here it is. So this one is the first one we looked at, right? Okay, so as you can see, at this point, this is 1.5. Okay, so this is the first part we look at the positive side, right? So you have the solution at 1.5. Okay, so as we are trying to get different values of x starting from this side, okay, we are approaching 1.5. And also this side, as you can see, if you get different values of x starting from here, no matter how far you go, you still be approaching 1.5. Now, look, we started at, what value did we get from the left-hand side? Okay, I think we got 1.6, which was very, very close to 1.5 itself, because this is 1.5 here, okay? This is 1.5, x got 1.5, okay? So we are very, very, very close to it, okay? So on one, we just have to do few iterations, then we reach that value. Okay, but here, because we started from 1, remember we started from 1 here, x go to 1, we have to move like, okay, we have to do several iterations here just to move from 1 to this root here, 1.5. We have to do several iterations. That's the thing. Now let's look at the negative one. Okay, the negative one. Let's see. So I've just put the negative there. Let's see now. So this is it. The negative one. Have you seen the reason why it's not approaching? Remember that we are trying to approach negative 0.5. So this is negative 0.5. Where have you seen? Here, where it's crossing the x-axis, right? Now look. Let's say we started from where did we start from first? We started somewhere at negative because of this, the nature of the slope itself, the way it looks. Looking at the nature of the curve itself, let me just define the nature of the curve. It's very different as compared to the other one where the negative, when we're the positive. Because when we're the positive here, very, very straightforward. Okay, if you're the positive here, You see the nature of the cave here. It's different, the slope, okay? Because the slope also matters. Okay, but anyway, don't even worry, you don't have to sketch this. I just want to see, like visualize it. The slope also matters. But this one was very, very straight slope. Okay, the slope was very straight. So no wonder it was very difficult for us to approach what? Negative, it's about negative 1.5 somewhere, negative 0.5 easily. And in fact, if you check, this is now something. If you check very well, properly, you notice that this cave doesn't actually cross at exact negative 0.5. Have you seen that? Okay. The solution is not exact negative 0.5. Okay, so this means that it doesn't mean that that 0.5 that was given in the question is the actual solution. No. Okay, but we should actually approach it. No wonder we're not actually getting the exact value of what? 0.5. And if you notice here, this guy crosses at this point, you can even find. Okay, after it's actually away from 0.5, as you can see. Okay, are you able to see it? Okay, it's very far from 0.5. It's very close to 0.55, but far from 0.5. So no wonder most of the values were actually very, very close, like around 0.53, 0.5, whatever around that. Okay, but if you look at the other cave, okay, the other one, okay, of the positive type. Okay, the positive type. Okay, you see this one is actually, even itself is not approaching, it's not crossing at exact 0.5, but if you look at it properly, okay, if you look at it very well, it's close to 0.5 to 1.5 as compared to the other one. The other one is not very close to what? 0.5. So look at this. Yes, it's not crossing exact to 1.5, but it's very close to 1.5. So the one, it was very easy for us to compare it. I don't know if that is making sense. Hello?
Yes, it is.
Okay, I'm saying for this one here, look at the way it's crossing the x-axis. It's very much close to 1.5, right? No wonder it was very easy for us to converge to 1.5. But for the other one, the negative one, okay? For the negative one, let me just put a negative here. Let me show you the negative one. Okay, if you notice here, we said, okay, we're approaching negative 0.5, right? That's what it says in the question. But if you look at the sketch of this guy here, it's very far from 0.5, but close to 0.55. So no wonder we had those roller coaster situations. Okay, it took a lot of iterations for us to approach 0.5 because the cave itself is not actually passing through 0.5. It's very far from 0.5. Look at the distance. Okay, just look at the distance itself. I hope that is clear. Hello?
It is.
Okay. Let's go back to our problem now. But here, you're supposed to do a lot of iterations for us to approach 0.5. Okay, a lot of them because of the nature itself. The cave itself doesn't pass through exactly 0.5. It's just close to it. Okay, it's just close to it. But the fact that we're not moving away from 0, we're just approaching it. But we won't reach there. It's not possible for us to get exactly 0.5 because the cave doesn't pass through 0.5 itself. Okay, it doesn't pass through 0.5 exactly itself. Even here, if you do the iterations from the first problem here, you won't get exactly 1.5 at some point. No, the cave doesn't pass through at 1.5 exactly, as you saw. Okay, but at least we're approaching it. Okay, we are approaching it, but doesn't pass through 1.5 exactly, or negative 0.5. So depending on how far the cave is from that route, it also determines how many iterations you're supposed to do. So here we did a few iterations for the first problem, for the first part, where we saw that we are actually trying to approach 1.5, but we're approaching it slowly as well. But here it was even worse. Okay, we're approaching negative 0.5, But now we're approaching it so slowly. At some point, we even moved away from 0.5 and all that. We are trying to approach something else. Okay, so you saw that you're approaching 0.55, 0.54, 0.53, 0.54, whatever. It's because you saw that the cave is actually passing at 0.55. So it can't move away from 0.55. Okay, that's where exactly the root lies, at 0.55. But in this case, it's a structure we need to follow. Okay, 0.5, but we can't reach that 0.5. We'll be just approaching it, we'll be getting close and close, or doing a lot of iterations. Anyway, I've said a lot of things. Let's look at something different. Okay. So if you have a question, please ask. Are we good to go?
Yes.
Okay.
It's only that I think it's cumbersome because
How's
you
it
have to
cumbersome?
do a lot of them for you to
Yeah,
just
I
be
remember
closer.
when we are starting this course, I mentioned that it's iterative, right? And iterative, we have to do it of a lot of iterations. And no wonder this question, most of them they are solved using computer. But you people be writing exam test using your hands. You won't be using your computer. Okay? Because you can just write a program that is going to produce different values, put them in a loop. Okay? You write a program that can calculate these values. Those people do C++ or MATLAB. Even MATLAB can do this. Okay. All right. And then the part B of the question, we've said a lot of things, so we're not moving fast. So part B of the question says, there is a third root near 2.6. Show that we do not converge to this root, even though values near the root, such as x naught equal 2.5 or p naught equal 2.7, are used to begin the iteration. So they're saying there's a third root near 2.6. Okay? There's a third root near 2.6. So we are given that, oh, there's a root near 2.6. Okay? So you see that these values that were given actually to us, in fact, I didn't even read the statement very well. So show that this converges to the root near 1.5. So it's not that 1.5 was the root. No, actually, so it's only in the graph itself. Near 1.5. And the curve wasn't actually passing through 1.5. But we have to show that, okay, we're actually converging near that root. And also, 0.5 is not a sure solution because that's not where the curve is passing through. But we are supposed to show that we are approaching near that. So now it's very difficult for us to get exact values because those values are not roots. We're just approaching near that. Okay. So this part says there is also another root near 2.6. Near 2.6. Okay. So we show that we do not converge to this root, even though values near the root, such as x naught, so given the initial values here, 2.5 or p naught equal 2.7. This is x naught also, p naught. 2.7 are used to begin the iteration. Let's see. So look, now there is a root near 2.6, right? So it's like the root is here 2.6. This side we picked 2.7. This side we picked what? 2.5. Now the question says we have to show that, okay, we are not actually approaching this 2.6. Instead, we have to show that, okay, we are diverging. Let's see. Because if they were diverging, it means 2.5 has to move away. When you're using 2.5, we have to move away from 2.6. Similarly, when you're using 2.7, you have to move away from 2.6. It means you are diverging, you're not converging toward this. It's the opposite. Are we together? So that's what we need to show. If you substitute 2.5, the value should be greater than 2.5. Sorry, less than 2.5. Less, so this 2.5 has to reduce, and reduce. Similarly, if you are using 2.7, okay, if you're using 2.7, we substitute 2.7, the value should be greater than 2.7. We are moving away from 2.7, where this value should get bigger and bigger and bigger. So it means that we're not actually approaching this. I hope that is clear. Is it?
Yes, it is.
Okay, so let's start. So we start with the x naught. So with x naught is equal to 2.5, let's see. So this will be our x1. So since this root is positive, right? So we don't need the positive part of that square root, right? We just need we don't need the negative part of the square root, because the root given to us on here it's 2.6, which is a positive number. So I have to use the positive root, okay? The positive function. So e, okay, so this is the square root of e to the power 2.2, so 2.5 over 2.
It's 2.4, 2.46. I was calculating.
2.46.
As 2.46804
804
5174.
5174. Oh, so you see that we've used 2.5. Now we're getting what 2.4 something. So we're moving away from 2.5 itself. So we're not even approaching 2.6. Let's get x2. Let's see. 2.468 over 2. Okay. You should get something smaller than 2.4.
Yeah, 2.42.
2 point what?
42
Mm-hmm.
89
89
255
255
44.
44. Okay. So this is now our x2. As you can see, x3, what is x3? E to the power 2.42, whatever, over 2.
2.3.
2.3, as you can see, this value is getting smaller and smaller, right? 2.3.
So 818
818
77
77, whatever there. Okay, you can continue. So let's also try this side. Let's use 2.6. This value should be getting bigger and bigger and bigger. So this is x1, e to the power 2.6 over 2 in the square root. Okay, so what do you get? If you use 2.6 this side, you get something greater. Oh, 2.7 if I not 2.6. We're using 2.7, right? Because we are
it's 2.7.
yes, 2.7. Okay.
Okay. Divided by 2. 2.72.
2.72. Whatever.
76 11
76 11
751.
751. Okay. And then if we use the same value now, e to the power 2.72, 76 over 2 to the power half. What are you getting as x2?
2.7655
0.7655
29
29
963.
96. So as you can see, we are moving away, we are diverging away from what? 2.6 as well. Whether we use 2.7 or we use 2.5, we are still not approaching 2.6. We're actually moving away from that. Okay, so it's more like we have this root here, 2.6. Okay, so this guy is moving this side, this guy was moving this side. As the values of x increasing this side, we are diverging away from that. Okay. And then part C says find another rearrangement that does converge correct to the third root. Up to now, since now we see that there's a problem here, there's no convergence, right? So now to rewrite our equation in a way that, we are going to converge to the third root, which is 2.6. By using those initial conditions, x not equal to 2.5 and x not equal to 2.7. Let's see. Let's go back to the equation. Let's rearrange it again a different way, other than using this square root the way it is here, that in this form. Let's try to rearrange the equation. Let's write in a different way. Okay. So what was our equation? Okay, which one is the equation here? This one here, right? This is our equation. So let's now rearrange it. Instead of us for solving for x squared, let's solve for e to the power x. So part C. So part C, we have, okay, part C, the equation, remember, it's e to the power x minus 2x squared equal to 0. Right? Let's see. Let's solve for this x now. Since we're already done with this x, Let's solve for that other x. Okay, so this will be e to the power x equal to 2x squared, right? Now remember that for us to solve for this x, we have to introduce natural log both sides. Natural log x squared, right? So this is remember the properties of natural log. Natural log of a to the power m. This is equal to m natural log of a, right? Don't forget this. So this is the same thing I'm going to apply here. So this will be x natural log of e. This is equal to natural log of x, 2x. In fact, this is 2x, 2x squared, right? Okay. Now remember that what is natural log of e is equal to 1, isn't it? Okay, so you end up having a natural log of 2x squared. Now let's try this arrangement. So this arrangement we're going to use now. So with the x naught equal to 2.5. See. So with x not equal to 2.5, let's see if we're approaching what? 2.6. Okay, so let's start. So x naught, this will be x1 now. Natural log of 2 times 2.5 is squared, right? Okay, so this is natural log. So what do you get? I don't know, me, I'm getting 2.5, 25, 728.
8644.
8644, yes. Okay, if you feel this is cumbersome, right, the natural log of 2x squared can also be written as what? This is a product. Remember that natural log of a times b. This one was our natural log of a plus natural log of b. You can also separate those guys, right? So that you just have natural log of 2 plus the natural log of x squared. Okay. Okay. Oh. You can also write like that. X squared, so this is natural log of 2 plus, you can drop these 2 here of natural log of 2 natural log of x, the same thing. So whichever version you want to use. So what is our x2? So we natural log of 2 times 2.525 whatever squared. So this is equal to what? So natural log of 2 times answer squared. I'm getting 2.546, confirm? 208.
Yes, 2.546.
Okay,
206.
or 206,
Two-
yes, yeah.
367.
36676, okay? And then you see what is happening, right? We're actually trying to approach 2.6, isn't it? We're trying to do that. Okay, whatever squared there, what you get? So natural log of 2 times answer squared.
Mm, 2.5623.
2.5623
56
56
285.
285. Okay. So you see you can actually try. You see that you'll be approaching 2.6. Okay, try as many iterations as possible until you are tired. Okay. Now let's also try 2.7. So with x not equal to 2.7, let's see if you're also approaching 2.6. Okay, so x1 will be equal to natural log of 2 times 2.7 squared. So how much is that?
2.679.
2.679
650.
650
727.
727. Okay, and then x2 natural log of 2 times 2.67 whatever 96 squared. This is equal to
2.66.
2.66
45.
45
201.
201
01.
0, 1. Okay, you can also try x3 now. Okay, you can finish the rest. Check them.
2.65,
So you see, this is reducing slow, right? 2.65,
31,
31,
95,
95,
114.
114. Okay, so you notice that we actually even this one was approaching 2.6. Even this one was approaching 2.6. So by just changing the arrangement of the equation can either diverge or converge. Okay, just rewriting in a different way, the equation can converge. Okay, so we have even seen here there is a convergence by just changing the order of the equation, the arrangement of the equation itself. Okay.